Okay, let's begin. So let's quickly recap what we did last time. Please submit your assignments if you have.
So the portal said that we could submit a PDF before this time on the LCCDE portal itself.
Portal said we could.
The LCCDE portal where the assignment page was posted, it said that we can submit the PDF file detailing our observations on the portal itself before 2 p.m. today.
So you've submitted already?
Yes.
Oh, okay. I don't know, maybe Parampreet by mistake he has done that. Okay. But from next time onwards, all assignments are only offline. Thank you. So we are reading about Z transforms. All of you know now what are Z transforms. We saw MFCCs, we saw discrete cosine transforms last time, and finally we came to time series analysis. So time series analysis means, just a quick recap on the important concepts. So we have three things. One is the DTFT, which is x of e to the power j omega, where e to the power j omega lies on a unit circle in the complex plane. And then we have x of k, which is the DFT. And all of you know DFT is a sampled version of DTFT. I sample DTFT in such a way, and those discrete samples form my DFT. The samples can, as you know, omega can lie between 0 to 2 pi. So my samples can also lie between 0 to 2 pi. If I'm taking n samples, then the distance between every sample will be 2 pi by n. Right? So that's the concept of DTFT and DFT. Now, where does the concept of Z transform come in? So we have got Z transform is when my Z does not lie, or my Z lies not only on the unit circle, but it can lie on the entire complex plane. My Z can be anywhere inside this complex plane. And then I have the concept of Z transform, and the advantage is that my series can converge, right? This series, a n e to the power minus j omega n, if my omega, this is for e to the power minus j omega, this may not converge. Let's say if my a n is, let's say, give some example. Let's say a n is 1. If let's say a n is unit step function, 1 always, then it will not converge. So therefore what we do is we, 1 will converge. No, it will be bounded, but not, but it won't converge. Let's say I have it, a is greater than 1. Right? A is greater than 1. Let's say it is 2 to the power n. This summation will not converge, because we know that from the infinite sum formula, this is something this. It will not converge if a is 2. But if we extend the concept of DTFT to Z transform, then I know if I choose my Z greater than 2, then this series will converge. So which means my Z should lie outside 2. That is my region of convergence. Means whenever my Z is in this region, then this term represents the Z transform of 2 to the power n un. So that's the concept of Z transform. Now let's see how this concept is useful to us. Okay, and we saw some commonly used Z transforms, like delta n is 1, delta n minus m is z to the power minus m, and u of n is u of n. What is the Z transforms u of n? Yes, unit step. What is the Z transform of unit step? 1 upon 1 minus Z inverse. Yes, so basically we have done it here. Right, when a is 1 upon 1 minus Z inverse. Yes. Okay, now let's see what is the utility of Z transform.
So in that case, do we have DTFT then?
DTFT won't exist. DTFT won't exist. Okay, let me geometrically tell you. Let's say if this thing is 2, right? And my DTFT lies on this circle, the unit circle, with radius 1. Right? So this means my DTFT would not exist, which means the uh, for the DTFT, my z lies on this unit circle, and here this term does not represent unit circle, or does not represent unit step function, right? So yes, so DTFT does not. But the advantage is that I can still work with this form. I can manipulate it, and then again I can go back to my time series, the time series representation of the unit step function or whatever the transformed time series comes. I can still work with it, but I cannot find the DTFT. DTFT will still not exist. Okay. Okay, if you want to learn more about the Z transforms, I can share some lecture videos with you, which were given by me maybe 2 years ago in the course Digital Signal Processing. You can really, these are very nice concepts, you can really learn them. But I assume that you know these beforehand. In case you don't know, just come to me and I will help you understand them better. Okay? But whatever I have covered in this class, right? So that is the scope for this course. I will not ask you that, I may not ask you questions which cannot be solved by using concepts discussed in the class. Okay? Yeah. But still, if you know the concepts of DTF, the Z transform, that will be helpful. Like I'm sure all of you have read about Laurent series in your complex analysis course, in your MTH course, right? You have read, right? Laurent series expansion. So it's exactly the same thing. Laurent series expansion is defined for different regions of convergences, right? That Cauchy theorem, Laurent's expansion, Taylor series expansion of complex functions, right? It's exactly the same thing. This is a complex function, 1 upon 1 minus AZ inverse is a complex function, and its expansion is, like, depending on the regions, it is different expansions. Okay. Now we are going to discuss the practical utility of these concepts. Let me open a new page. Okay, now we are going to discuss about linear constant coefficient difference equations. So what are these? Let's say, okay, let me write down an equation, then you tell me something about it. Y of n is equal to A times, let me call it P naught, what is this? My y of n is some constant times x of n plus some constant times x of n minus 1. It's a filter. What kind of filter is this? Kind of moving average filter, right? It may be doing a weighted average, kind of moving average filter. So, but the interesting thing is, my y of n does not depend only on x of n. It also depends on x of n minus 1, which means it has some memory. It has some memory. Is it a causal system? What is the meaning of causal system?
You don't need the future values of x.
Yes, causal system means I can give you the output by seeing only the current and the past inputs. I don't need to see future inputs, right? Can you give an example of a real world causal system? There are so many, just feel free to share. Microphone, very good. Let's say what is transmitted on the speakers, it only depends on what I'm speaking now and also what I spoke in the past. It may have some echo effect or some those kind of reverberation kind of things, which means my current output depends also on some past inputs, but it certainly does not depend on the future inputs. It does not know what I'm going to speak next. So microphone is a very good example. Any other example?
So aren't all
Life. Okay. Okay. Yeah. Yeah.
aren't all
Well,
real
I kind of I may construct some hypothetical examples. For example, you came to IITK because you want a degree. Yeah, but I don't know. Maybe still you're projecting. Yeah, yeah. Okay, fine. I'll not debate on this. Yeah. What else?
So aren't all practical, I mean, physical systems?
Yes, exactly. All physical systems, more or less. I don't know any non-causal physical system.
Sir, does the translation system will count as a causal or non-causal? Because, like you are writing a statement in some language and it is getting translated, but as soon as you change the like upcoming context, the whole translation changes.
Very good, very good. This is an example of a non-causal system, which means I cannot do a translation on the fly. Which means I cannot, I need to know the entire thing and then I can do offline processing. Online processing is kind of, I can fake it or I can kind of do it, but then still I will have to revise it later. So I'll give one very good example from linguistics. Okay, you keep translating the sentence. Translate it in real time. The army sent past the borders. No, no. The
Better you speak in Hindi, we translate.
no. I will speak. The the horse ran past the stable. Okay. The horse ran past the stable. Maybe I'll write down. Okay, boundary. The horse ran past the boundary. Translation? अच्छे से बताओ
पूरा सीमा नाम के पास है।
वेरी गुड जो घोड़े को सीमा के पार भगाया गया था वो गिर गया जिस घोड़े को सीमा के पार भगाया गया था वो गिर गया
Then there should be an that.
वो इंग्लिश में दैट नहीं आता मतलब इट्स नॉट नेसेसरी टू पुट दैट इन इंग्लिश राइट द हॉर्स रैन पास द बाउंड्री फेल डाउन these are called garden path sentences right these are called garden path sentences so it's in these sentences if you try to do kind of causal translation you will be in trouble but basically you need to see the entire sentence and then only you can do the translation okay so this was just an kind of detour but I hope this will be something interesting acausal systems in the real physical world finding acausal systems is not okay so this is a causal system because it depends only on the current input and the past inputs now if we try to do can you write the filter in terms of its Fourier transform or impulse response what is the impulse response of this filter quick what is the impulse response of the filter yes so what is the meaning of impulse response means my input is an impulse function so my y of basically y becomes h of n right this is equal to delta n minus, no, delta n times p naught. Is it an LTI system? Is it an LTI system? Yes. So all the LCCDE, linear constant coefficient difference equations, they are LTI systems, right? So you can also verify, but it's also you can kind of just memorize, but it's easy to verify. Okay. So this is an LTI system, causal. Now, what is the Fourier transform? So generally, whenever we have such systems, it's very easy to write here Z transform. So what is my H of Z? P naught plus P1 Z inverse. Right? Very easy to write the Fourier transform of, or the Z transform of this equation. So this Z transform, if you look at the complex plane, in this complex plane, if you remember your complex analysis course, two things are very troubling for an analytic function. Analytic function means a differentiable complex function. It's a differentiable complex function, right? Therefore, it's an analytic function. But there are two things which we have to be very careful about. They are the poles and zeros. So what are the poles of HZ? There is no pole. Oh, there is one pole. Because it's P naught Z plus P1 upon Z. It has got one pole and one zero. Where is the zero? Minus P1 upon P naught. And where is the pole? Pole is at 0. So these poles and zeros are most important things in an analytic function. And just by defining the poles and zeros, I can define my H of Z if it is in this rational form, right? So here I have a pole here, and 0 may be minus P naught upon, no, minus P1 upon P naught somewhere. If they are both positive, then something here, right? Okay, just an extra note of information. In case you remember your linear algebra course, or sorry, the digital signal processing course, is this system stable or not? Is this system stable or not? So the system is stable means if my input is bounded, my output will also be bounded. BIBO stability, bounded input, bounded output stability. So if my xn is bounded, will my yn be bounded?
Yes.
How do you know?
P naught and P1 are finite, then it cannot exceed P naught plus P1 times m. Then m is the bound for x.
Yes. So basically you assume that x of n is less than, or mod of x of n is less than some m, which is certainly less than infinity because it's bounded. So then you will say my P naught x of n plus P1 x of n minus 1 bound. This bound is always less than or equal to what? You know what is this called? The Cauchy-Schwarz inequality? A triangle inequality. Triangle inequality says P naught is constant, so okay, mod P naught times mod of x of n plus mod P1 times x of n minus 1 mod, right? And this right hand side, this is equal to P naught times, or P naught plus P1 times m. So which means which is less than infinity. So it's also bounded. So you can prove that this is a bounded system. Now there is a shortcut to detect or to tell whether the system is stable or not. Anybody knows the shortcut?
Zeros are left.
Zeros are in, poles are in the poles are inside the unit circle.
Yes, very good. So that what you are saying, that is true for Laplace transform, but we are doing Z transform. Laplace transform is for the continuous time signals, but this is a Z transform, it is for the discrete time signals. So here we consider the unit circle. So my unit circle, let's say this is my unit circle. the condition is all my poles should be inside my unit circle. If that condition is satisfied, then the system is stable, right? For such a system, like when hz is a complex function, all right, it's a stable system. It's because all the poles are inside the unit circle. Now see, by placing my poles and zeros appropriately, I can design my filter, right? If I want to design a filter which amplifies certain frequencies and suppresses certain other frequencies, I can very well do that. For example, I'm hearing this AC noise. Can you design the filter for this? Design a real-time kind of real-time microphone system which will just filter out this AC noise. Can you do that? Quick. Just rough idea. I don't need the mathematical details, but just the rough idea.
First we can figure out the fundamental frequency of the
Okay.
noise, and then we can,
How will you find that out?
we can just record it and then observe the spectrum and find peaks in the
Yes.
spectrum.
Yeah. So probably look at the spectrum. Spectrum will have, it may not have fundamental frequency, but okay, high energy in certain
In
frequency regions,
band of
certain band.
frequencies, and
Yeah, and then you want to suppress that
so
band.
if there are isolated peaks, you can do a notch filter there, and if there are band of frequencies, you do a band pass.
Yes, yes. So basically, generally, it's a very high frequency kind of noise. So I assume the spectrum will look something like this. It will have here low amplitude and suddenly high amplitude, something like this. So I want to suppress this region, which means this is my x of f. Oh, sorry, x of f. I want to suppress this. So what I will do is I have to design a filter which is something like this. It should allow the low frequencies and it should suppress the high frequencies. This is my h of f, right? So how do you design such a filter? Yeah, so when you look at this Bode plot, yeah, Bode plot. But okay, I will not confuse with the Bode plot concept. In case you remember it, it's very good. If you don't remember it, no problem. Take the unit circle in the z-plane, right? And this frequency, let's say it corresponds to some value here probably. Because when you discretize it, this will become some discrete frequencies, right? Let's say my next copy will appear somewhere far, right? So I'm assuming that aliasing is avoided. So I want to suppress this frequency. What you will do? I put a 0 nearby, right? And you want to boost these frequencies, put a pole somewhere here. This pole will boost this region because my Fourier transform is along this axis. No? So I will put a pole somewhere to boost this region and put a 0 somewhere to suppress this region, right? There are other details which you can go through, like how do you make sure that phase is also not distorted. So which means you put poles and zeros in some fashion that the phase is not distorted. But okay, this is the general idea that you can, by putting a pole, you are enhancing a region around it, and putting a 0, you are suppressing the region around it. Okay.
So why is it 0 exactly on the unit circle?
It can be on the unit circle also, no problem. It can be on the unit circle also. It can be outside the unit circle also. Zeros can be anywhere. Just the poles have to be inside the unit circle for stability. Okay, I will now move to the next thing. I'm just telling you that how important is this, how important are poles and zeros, or how important is the concept of Z-transform for real-time signal processing, right? This is a real-time filter. You can implement it in real time. It's very fast. If you try any other kind of filter, it may be slow, but this filter is very fast. You can even implement it on a device, on a hardware. Okay, so let's study this LCCDE in a little bit more detail. So we have got general form of LCCDE is like this. My y of n is p0 x of n plus p1 x of n minus 1 plus so on plus some pm x of n minus m something, means it's just some number, means m, some finite number, plus, oh, before I go to this form, let me also write something else. Yeah, before I go to this, now consider another kind of y of n. Y of n is what about this? What kind of filter is this? Yn depends on current input and also on the past output. It is a feedback, right? So my past output is also affecting my future output.
So would this be a AR on Y?
Autoregressive, yes. This is called an autoregressive filter. Autoregressive means it regresses on itself, which means it uses its output, or it uses its past outputs to find the current or future outputs. It's called an autoregressive function, autoregressive AR function or AR filter. Okay, now tell me, how will the h of z look like? How will the h of z look like? Okay, so let's compute it. Y of z is equal to p naught times x of z minus d1 times y of z, z inverse. So yz goes to the other side, so it becomes p naught x of z divided by 1 plus d1 z inverse. So what is my h of z? P naught upon 1 plus d1 z inverse. Where are the poles and zeros? Sorry, I didn't hear.
Minus D1
What is minus d1? Pole is at minus d1. Let's say d1 is positive and it's smaller than 1, so that system is stable. Yeah, so pole is minus d1. So basically you can write it as p naught z upon z plus d1. Right, so pole is at minus d1 and 0 is at 0.
So how did that y of z into z inverse?
Okay, if y of n has a z transform y of z, then y of n minus 1 will be, the z transform will be, we saw it in the previous lecture, no? At the end. You can derive it. You can derive it from basic equation. Right. It's very easy. Just you have to do assume put n minus m equal to k. That's very simple, like the way the usual stuff. Oops. Okay, so what do you find here? You find here, in the previous case, in the in the moving average kind of filter, you could have your poles only at 0. Right? In the previous case, no matter how many terms you add here, p naught plus p1 z inverse plus p2 z to the power minus 2, so on and so forth, your poles will always be at 0 only. To control the poles, you have to add autoregressive component. By adding autoregressive components, now you can place your poles anywhere, right? So that's the catch. So this is the thing. So in general, it becomes this way. Oh, with a negative sign. Negative sign is useful because then we'll get a positive in the Z transform. What is the Z transform now? H of Z. What is H of Z? H of Z is basically y of Z upon x of Z. This is equal to what? P naught plus P1 Z inverse plus so on and so forth, P2 Z to the minus 2, etc. Pm Z to the power minus m divided by 1 plus D1 Z inverse plus so on and so forth plus dn, it should be dn Z to the power minus n. That's it. Right? Clear? And now I know that this is a polynomial equation. The denominator is a polynomial equation. By factorizing it, you can find the roots of this equation, and those roots are the poles of HC. Those roots are the poles of HC. And likewise, you can factorize the numerator, you will get the zeros of HC. Right? Okay. Anybody has got any questions at this point of time? Okay, so I think the take-home message of this section is that by adding this autoregressive terms, we are able to place poles anywhere at any point other than the zero, other than the origin, and in this way we are able to design more powerful filters. But what is the cost you have to pay? I don't know. If you just make sure that the poles are inside unit circle, you are good to go. Right? What is the size of memory needed to implement this filter? Memory? Yes? No, okay, this filter, sorry. This simple filter. Yn is P naught xn minus D1 x yn minus 1. Huh? 3. Okay, you can assume that you have xn has just come in. Okay, I will say, okay, assume that it's not consuming any memory, it is the current input. Okay, just assume. And then only the past inputs or the past outputs need to be saved. So what is the memory size you need here? 1 only. So only one past value you are saving. And in general, what is the memory size needed? Somebody told m plus n. Right. So m plus n is the memory needed. Yeah, that's it. Okay.
So should we consider the storage space for current input, or
yeah, we are not considering it at the moment. If it is there, then you just add 2 for the current input and current output if you want to consider that. But if you don't consider, then it's fine. M plus N is the. Okay, now tell me one question which is very important. My Yn can hold information about the past. Okay, let's first consider only moving average model. My Y of n, so basically all D's are 0. All D's are 0. My Y of n can depend on past inputs. How many past inputs? My Yn can depend on the past inputs. How many past inputs? M past inputs. Now if I add autoregressive terms, my Yn can depend on how many past inputs? 2M? M plus 1? M plus N? Okay, let me help you. Let's say something happened, like X takes some value, input takes some value, right? My this X1 is something, Y1 will depend on X1, right? Now my Y2 depends on Y1, Y3 depends on Y2, and this chain goes on. And my Yn could be very large, millions also. It depends on X1. So potentially it can have infinite dependence, right? It can have an infinite context, potentially, right? Which means my Y of n can depend on X of minus something or X of 0, let's say, where this whole thing started, even when my n is very, very large, right? So this thing clicked to some machine learning people who felt the necessity of a longer context. For example, when I'm speaking something and you are just writing it down, not translating, just writing it down, right? So how much context you may need? Just if you look at the current word only, that's sufficient, no? Right? But sometimes you may say, no, I may need longer context, because if I have some ambiguities, I can resolve them by having a longer context. For example, when I say some word is ambiguous, then you know that, okay, after I cannot have is. We will have am only. So in case you have any ambiguity or doubt, you can consider, okay, before this was I, so now it should be am, or but it certainly cannot be is, right?
So for example, variable declaration will always be ambiguous.
Variable declaration means?
For example, if you say that we assume X is, until you do not say is this, we cannot do anything about the X. It will just be written.
Yes. So I will say, let us take X equal to 2. Now we square it and then we add 5 to it and then we do this. Tell me what is the answer. So you have to know all the way back to what is X. So long-term dependency is there. I'll tell one example here. Let's say, अध्यापक ने लड़की से पूछा, क्या तुम घर जा dash? What should come? जा रही हो, right? रही हो, right? So you will not say रहा हो, you will not say रहे हो, you will say रही हो. Why? Because long ago he said लड़की. अध्यापक ने लड़की से पूछा, right? So in this way, when we do tasks in machine learning or in machine learning, we need long-term dependencies, whether we work with audio or text or videos. So whenever we have a time series, the signal is evolving with time, then we may need the context. Microphones don't need context, right? Microphones just need to amplify the current instant and they don't worry about the past. But many tasks, like I told you some example, like ASR, language understanding, NLU, natural language understanding, they all need the context. So therefore, this idea of autoregression, it's very useful. Because if you okay, now let's start with this topic. So when you want to apply machine learning for time series data, which means it is constantly streaming in with time, then what can you use? What kind of machine learning models can you use? Okay, whatever you have studied in the past. You have studied dense networks. Can you use dense networks? Why? How?
You can model it as an n-length vector and
Okay, but then another n+1 entry will come. What will you do? Then you will have to change the size of your network.
maybe you can window it, consider a finite length window.
Yes.
And if there is no input in, or
Yes.
it's basically 0 or some input for edge cases.
Ignore the edge cases. Like assume it's a constantly running stream of data. Then you take a small window. If you take a small window, and then you will be kind of assuming it's an LTI filter, and this window is like an LTI filter which has a finite window, and what is it in terminology of signal processing? It's a filter. It's a filter with a finite impulse response. Right? It is a finite impulse response filter. Which means if my input is something, then my output
How is it finite impulse response in this machine learning example?
my output y of n depends only on finite number of past samples. Let's say it is p naught x of n plus p1 right. It has a finite what is impulse response? You are convolving x with h. So in this case, what is my h? Tell me for this filter what is h? You have p naught delta n, p1 delta n minus 1. And what is yn? Yn is the convolution of that h of n with x of n. And that's why you obtained this. So the impulse response is finite in length. Finite length impulse response. So, and it's a convolution. You're convolving this filter h with the time series. As the time series is progressing, as your time is moving forward, you are convolving, right? What machine learning module can you use to simulate this, to emulate or to implement this? What machine learning module from your machine learning knowledge can you use to emulate this? Markov model is a general probabilistic model. It may be implemented with machine learning or maybe with other things also. But I'm asking only for neural networks.
The normal weighted linear combination. P0 to Pm would define the weight matrix, and x and to xn minus n will be the n plus 1 length window.
A dense layer, huh? Okay. So actually, you can use a one-dimensional CNN. One-dimensional CNN. Because if you look at single kernel of CNN, it is like a dense network only, but it's a kernel because it's scanning the whole thing, like convolving with the whole thing. So this is the one-dimensional CNN you can use. Oops. 1D CNN corresponds to the finite impulse response filter. It's like a modern terminology for finite impulse response filter. Okay. Now, but you know that basically this equation LCCDE, which my 1D CNN is emulating, this is a kind of moving average kind of thing. It has a limited context, limited dependence. What else? It has let me write it has a finite context, which means the dependence is finite. What else? Yeah, basically. Okay, but I know I can increase my dependence by adding autoregressive terms, which means if I choose my yn to be not just p0 xn so on, if I also say minus d1 yn minus 1 minus d2 yn minus 2. So this is where the concept of recurrence comes in. This is the meaning of recurrent neural network, or this is where the recurrent neural network became popular. So I want to make my yn dependent on not just x of n, but also my past y of n. So let's define a function like this. So this is my x. I'm calling it t, but you can call it n also. Or should I call it n? Let me call it n now. Why to call t? We are doing it with n. But now see, this is a vector. My x of n is a vector. Right? It's not a scalar, it's a vector. And h of n is also a vector. It's not a vector in time, it's the vector of features. We can say spectrum or something. And then this is. So this is a simple dense network, right? Or you can call it a 1D CNN if my n is kind of changing. You can. No. Yeah, you can call it 1D CNN, but its kernel length is only 1 then. Okay, anyways. So where is the concept of recurrence coming in? If my, okay, let me write the equations first. So what are the equations here? My h of n is equal to, is a nonlinearity, sum x of n plus some v, right? And my y, let's call it the y hat. Y hat of n is some other nonlinearity, could be softmax or sigmoid, some other right. Is this clear? Okay, quick exercise. Let's say my x has 10 units, h has 5 units, y has also 5 units. Tell me the size of u. 5 cross 10, b 5 cross 1, right? And likewise my v is 5 cross 5 and c is 5 cross 1. Okay. Okay. So what is the meaning of recurrence? Recurrence means now I have a time delay thing or a memory element. In signal processing, we call it as Z inverse. Z inverse is what? Delta n minus 1, right? So you multiply it, so you get here h of n minus 1. So basically my h of n, okay, plus some W times h of n minus 1 also. So my h of n depends not only on x of n but also on h of n minus 1 plus b.
Would the recurrence happen before applying the non-linearity or after? Because in this case, then there would be an inverse function relation if we want to simplify it.
If you want to,
So, for example, in this case, if we want to simplify or analyze this, then there is an inverse function dependency between these two.
What is
Between
it?
the recurrence, the past term and the current term. So, is the recurrence element coming in within the, is the non-linearity being applied on the recurrence element, or does it occur in addition after the non-linearity is applied to the x part and then we add it?
no, f is applied after you add ux and wh. Means so, okay, I think I should write it completely. So it is f of ux, I'm skipping the ends. Right, so it is like this. You add them linear affine functions, and then you apply the nonlinearity. And likewise, yeah, in y we are not putting any recurrence unit, so it remains the same. So y hat still is the same. Only my f has changed. This is an example of a recurrent neural network. This is called a recurrent neural network. It has what do you call recursion or autoregression. Right? You can call all those terms. Fine. Now, what is the advantage? Advantage is that you can have very long context inside this recurrent neural network. Now, let's analyze this equation in a bit more detail. My h of n is a function of ignore xn. Xn is there, okay, but I'm not interested in x of n. I'm just like put it separately. Let's say my h of n is a function of h of n minus 1, but my h of n minus 1 is itself a function of h of n minus 2. My h of n minus 2 is a function of h of n minus 3. Right? How long should I expand it? Okay, why I'm doing this exercise? In order to train this network, I need to find the derivative of h of n with respect to theta. Clear? To find the gradient descent, to do gradient descent basically, I need the gradient of h with respect to theta. Right? Because I will have some error function which is a function of y, and to find gradient of that error function with respect to theta, I need to do dou e upon dy and then dou y upon dou h, then dou h upon dou theta. Right? And theta is basically v, c, u, b, all these are theta. Right? So what is theta? Theta basically, no, not belongs to, it is the set. V, u, w, c, all these unknown parameters, they are theta. Right? To compute how will you compute dou h upon dou theta? Because you will say dou h upon dou theta is equal to derivative of f with respect to theta plus derivative of f with respect to h and derivative of h with respect to theta, because h is again a function of theta, right? That's how we do it, right? Chain rule. You first differentiate f with respect to theta, then you differentiate f with respect to h and h with respect to theta, right? So this h is h n. Now what is dou h upon dou theta? It is again the same thing. No, this is hn minus 1 now, sorry. Oops. Right? This was n. Right? And dou hn minus 1 upon theta is again a function of dou hn minus 2 upon theta. Right? So which means this derivative will again be equal to dou f with theta plus dou f by dou h and dou h n minus 2. Oh, sorry, this is n minus 2 here. And again, this thing has to be expanded. How long? How long can we do it? How long can we keep unrolling it? So the answer is, you assume that, okay, I will do it only till 5 steps or 10 steps and I will not go beyond that, right? So you unroll it only up to 5 steps or 10 steps, and then you say dou h upon dou theta is 0 now. What else can you, how long can you keep going? Because you know that this dou f upon dou h, it is also kind of curtailing the effect. Generally dou f upon dou h, dou f upon dou theta is, dou f upon dou h is generally, maybe if it is less than 1, then it is kind of reducing the effect of your dou h upon dou theta, right?
Is this dou f by dou theta or dou h by
This one is dou h upon dou theta. Now I wrote h as f of h comma theta, right?
Just wrote h as f.
This is minus 1. Huh? No, f is different. F is this. H is f of h n minus 1 comma theta. Right? Is that clear? Clear? That's it. So this is what we do to train our Pardon?
There should be a plus sign. It's basically equal to something.
Oh, I'm saying that this term is equal to.
No,
Plus.
What is that? Del f?
There shouldn't be a plus.
should be equal to that.
Oh. I mean, in the first term, this first term,
Yeah, before that there's a plus sign in the middle.
this term.
Yeah, before that there's a plus sign. Partial.
Okay. I think I got your point. Why will there be a plus sign? Good that you asked the question. Now see, f is a function of theta and also a function of h. Okay, let me take an example. The best way to resolve this is take an example. Let's say my y is, no, not y, it's h. Let's say my h of n okay. Now tell me what is derivative of hn with respect to a. Or b also is fine, but okay, let's remove b. Just take this much. What is derivative of hn with respect to a? Yes, this is equal to, first you take h of n minus 1 plus a times derivative of hn minus 1, right? That's how you will write, no? It's hn minus 1 plus a times derivative of h minus n minus 1. That's what I wrote here. This is basically derivative of f with respect to theta, assuming hn is constant. Okay, actually I should write there. So assuming, hn minus 1. Right? So assuming hn minus 1 is constant, you take the derivative of this function of theta, plus then assume theta is constant and take derivative with respect to h only, that I have written explicitly. This means that derivative of f of h assuming other things are constant, and then into the derivative of h with respect to theta. Right? Does that make sense now?
Right, because there is a multiplication between theta and hn minus 1.
Theta, h and?
Theta are the parameters.
Yes.
There is a multiplication between theta and hn minus 1.
Could be multiplication or whatever, doesn't matter. I can give you another example where let's say my h of n is h of n minus 1 plus b. Now write down what is derivative of h with respect to b. This will be equal to what? 1 plus derivative of h of n minus. The same thing, no? Whatever the function is, we say that assume hn minus 1 is a constant and then take the derivative. Okay, so this is called the training of recurrent neural network, and this algorithm is called backpropagation. All of you agree this is backpropagation? Backpropagation, right? Through time. So you are backpropagating through time. From n you went to n minus 1, from here n minus 2 to n minus 3. So you are backpropagating through time, not only through space, but also through time. Space means layers. Not only through layers, but also through time. Right? This is called BPTT. BPTT algorithm, which is nothing else, nothing other than gradient descent algorithm, but just a fancy name because it's recurrent neural networks are popular, so training them is also a popular thing. So just give it a name, BPTT. But if you look at it geometrically, or what do you say, graphically, how it looks like. Let's say you have a network. This is at nth instant. Minus 1th instant. And because of the recurrence, you have this connection. Right? Which means my h of n depends on x of n as well as h of n minus 1. My h of n minus 1 depends on xn minus 1 but also on h of n minus 2, right? So which means if I have a parameter theta, every connection has got some theta, right? So let's say, following the previous notation, what was the notation we used? U times x plus w times h. So I have here u times x and w times h. And w appears everywhere. U also appears everywhere. So if you want to compute here derivative of y, let me use Newton. Oops. You want to compute derivative of w, then you have to compute not just through this path, but also through this path, but also through this path. So you are back propagating through time, right? All these terms will appear. And you can decide, okay, I want to unroll it for last 5 steps, for 10 steps. That is up to you as a hyperparameter. That's it. This is recurrent neural network. Okay, now okay, assuming, let's say my dou f upon dou h is a number, let's say it's just 5 or something, let's say 0.5, then if you actually keep expanding it, it is 0.5, then this thing will multiply here again, so 0.5 square, 0.5 cube, 0.5 power 4, so it is exponentially decaying, right? Which means kind of theoretically I can say that it has infinite dependence, but practically this dependence is exponentially decaying. So my dependence is not actually doesn't go very far. Can we do something to make my dependence really far? And that's how the concept of LSTM came about. That let us use long short-term memory. Yes, I have short-term memory, but it is really long, which means it really extends far back in the context, far back in time. The concept of LSTM came. I will not be discussing LSTM in this class now, but I will share a video with you which you can watch. It discusses RNNs and LSTMs. It's a very simple concept. So if you understand this graph, then understanding LSTM is very simple. Why? Because the LSTM has only a few more nodes here and few more connections like that. Means this node depends not only on H, but also depends on a previous node. And the only thing to notice there is that these weights are not constant. They are also a function of previous inputs. Or no, not previous inputs, but current inputs, let's say. These weights are also a function of current inputs. That's the only difference between normal RNN and LSTM. LSTM is also kind of RNN, or the RNN which we have discussed here, and the LSTM. The only difference is that you have few more nodes, and these weights are not static, are not constant, but they also depend on inputs. When W is a function of X, and something else also, maybe H of N or something. That's it. So what is the advantage? The advantage is that these gates can shut themselves out whenever they see something appropriate in X and H. That they learn that, okay, this is an X of X and H, this is an important information, let us shut ourselves out so that later we can open up and then we can pass on that information to Y. Right? And then they may when they see some appropriate X and H, they will forget, or means they will dissipate that information. They will lose that information. Okay. So one thing which is important here to note is, yes, my RNNs have got potentially infinite memory, you can say, or dependency, but they do a lossy compression because my H of n has a finite size. A 10 cross 1 vector, even 100 cross 1 vector, even 1000 cross 1 vector, but still it is a finite length vector. Potentially it cannot save infinite information, right? Given that our precision is also limited. Does that make sense? So, therefore, RNNs, even if potentially or theoretically they can have infinite memory, but they do not have. They do not have, practically they cannot save very long context, RNNs. But with LSTM, we try to make some packets, like some context information which can lock the information and release it whenever required. That is the concept of LSTM. And then likewise there is a concept of gated recurrent units, GRU, which is also like LSTM but computationally a little bit less complex. Computationally less complex, but it also uses the same concept of locking in the information by making my gates as a function of input and hidden state. Yeah, that's it. So if you want to know the details, then I will share the lecture with you. But I think, or you can read the original paper also. That's very simple. Okay, you have any questions? Do you have any questions? Okay, one more thing I want to tell. The CNNs, they are computationally a little bit inefficient, but LSTMs are computationally very efficient. Why? Because RNN or any kind of RNN, you can process the incoming signal on the fly. You don't need to go back. You just process it in one direction. So it's very efficient. Yeah, 1D CNN also is efficient in that sense. Okay. Yeah. Okay, but in 1D CNN, if you want a long context, you will take a very long filter, then it becomes computationally inefficient. But with recurrent RNN, it saves the information. It kind of saves the information in its hidden state. So computationally it is more efficient. Yes. So this is a well-known fact that RNNs are computationally more efficient than CNNs, right? But performance-wise, CNNs may supersede RNNs. CNNs may supersede RNNs for many applications. Why? Because RNNs, they just scan it once, but CNNs can scan multiple times because every layer is scanning. Every layer is scanning. So this is my experience that CNNs give better results, but the downside is that CNNs cannot be used in real time and RNNs can be used real time. Okay. The other thing is about parallelization. In CNNs, let's say this is my spectrogram. This is my spectrogram. If I'm applying RNN, then I will just scan it once. 1, 1, 1, 1, 1. That's it. The answer has to be there, right? Let's say if I treat this as my x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, then my RNN will give me correspondingly y of 1, y of 2, y of 3, y of 4, y of 5, y of 6. And my CNN will scan the whole thing and it will also give me these numbers, right? So in this context, I'm saying CNNs can be computationally a little bit more expensive, but their performance could be better than LSTMs. But LSTMs can be used in real-time applications. So the assignment which you are doing, you can use LSTMs also. I have shared the assignment in the shared folder, and I've also shared some practice problems in the shared folder. Go through them, and all the best for the exam. If you want extra session for discussing some doubts, you are welcome to do that. Just let me know when you want to come. If there are less number of students, we can meet in my office. If there are more students, we can book a classroom.
So what is the syllabus for the exam?
Everything done until today, including RNNs.
LSTM.
LSTM, I may not ask you details of LSTM, but whatever we discussed today, that much. But if you go through that lecture, that you may get a better understanding, and it may help you to solve some problems which you may see in the exam. Okay. No questions? No doubts? Okay. Thank you. Oh, just a minute. I'll just discuss today's assignment solution. It will take 2 minutes. So, all of you submitted the assignment, right? Okay. So, when you hear, how did you do it? By listening? By listening? How did you use Prat?
Difference between each bit. I use the difference between first and fifth beat was usually 2.4 seconds in all of the videos. So I thought each beat will be around 0.6. So if at a 0.6 there is no beat, then I put a dash there. And if in that if there is a beat at a stroke at 0.9. Then it's a dash and then.
Okay, so I'll tell you how I do it, and it's very efficient. This is when I tried to do it first time a few months ago. I failed miserably because I didn't know how to. Because I am not expert like Parampreet, who made the assignment. He can hear and tell, but I am not a musician like that. So what I did is I used Prat and tried to do. Was not able to do it, but then something clicked that okay, this is a good method to do, and I'll just share that method with you. So let's say it is tin tin dha, there's something. So generally you can look at the spectrogram or the waveform in Prat, and you can detect the onsets visually very efficiently, and because you hear them, you also know what label they carry. Let's say this is tin tin dha. And then there is this periodic signal will repeat. If you notice, there were several cycles. So why there are several cycles? To help you understand that what is the start time and end point of one cycle. So let's say I start here and I end here. This is also tin tin dha. Right, this is my complete cycle. Now what I do, I will note the timings. Let's say this is 1.2 seconds. This is 1.5 seconds. This is something I don't know what. And this is again, tell me some proportional number. 3 plus 6, 2.4. So what I will do is, I will write down, I make a table first. I'll make a table. I will say the name, and then the onset time, then again the name, again the onset time, again the name, again the onset time, and again the name and the onset time. Now I know this should map to 0 and this should map to what? 4 beats, right? 0, 1, 2, 3, yes. This should map to 0, this should map to 4, which means first of all I subtract 1.2 from everything. Let's do that first. So minus 1.2 from everything, so it becomes 0.0, 0.3, 0.6, and this is, and then you multiply with 4 upon 1.2, whatever that comes out to be. How much will that be? 40 upon 12. So 10 by 3. 10 by 3, so 3.3. So multiply with that. So how much it becomes? 0? And this is? Got it. Right? Now if there are half beats or something, it will become 1.5 or something. And now you know how to write it, right? This is the first beat, this is the second beat, and if it were 1.5, I would have said dash comma this, because it starts at 1.5. So this is the method I used, and I found it very, very efficient. Okay, in the exam you can use it. Thank you.